So we're going to look at systems. In general, our systems will look like this. Be something to the effect of x prime is equal to ax plus by for some real numbers a and b. And then we'll also have a y is equal to, or y prime is equal to cx plus dy, also for real numbers, c and d. Sorry if I keep stopping or go silent for a second. I have people coming in. It keeps giving me a little notification. Okay, so this is our system. It's a system of differential equations instead of just having one diffie-q. They're both first order, and because of that, you can analyze them geometrically in a nice way. Because when you say x prime is equal to something, you're just saying that you have a set of slopes, essentially. At each point, x and y, you have a slope for x. You can decide what that the rate of change of x is, and at every point x, y, you have a slope for y, or rate of change for y. Putting those together, you can track solution curves through an xy plane. Now, one thing that will be particularly helpful is to take each of these and find out where they're equal to 0. That'll be called finding the Nullclines. So the Nullcline, that'll be where x prime is equal to 0 and y prime is equal to 0. Now, what that means is, for example, in the case of x prime, that you can take ax plus by, set that equal to 0. In fact, let me arrange these a little bit. I'm just going to switch the sides here. Same over here, just so that it's kind of aligned nicer. And we can see that setting x prime and y prime equal to 0 gives us, because of the equality of x prime and y prime up top here, we end up with ax plus by is equal to 0. We end up with cx plus dy is equal to 0. With a little bit of rearranging, what we get is this. And if this makes some sense to you, or hopefully at least it sets up the idea in your mind, that it'll make the first part of this lab, I think, pretty straightforward. That what we're doing when we set x prime equal to 0, we're setting ax plus by equal to 0, and then a little bit of algebraic rearranging gives us that negative a over bx is equal to y. And how did I come up with that? Just basic algebra, nothing crazy. Subtracted ax from both sides, divided by b, provided that b is not equal to 0. And then the same thing over here with the y prime is equal to 0. We have negative c over d, x is equal to y, provided that d is not equal to 0. So these give us the Nullclines. In general, they'll look like this, but if it helps you to see it more in terms of the notation we're used to when looking at lines, it looks like this. And these, of course, are just straight lines. Now I'm going to color these. I'm going to color these like so. I'm going to color this one green and this one red. And the reason I'm coloring them is to match up with the applet that we'll look at shortly. Now, if we think about graphically what this red curve looks like, what this is saying is that there's no change in x. The change in x with respect to time, let's say, is going to be equal to 0. And maybe it's worth mentioning back up here that x and y you can think of as both depending on t. So when we're looking at x prime, we're looking at the change in x with respect to t. But there isn't any. So what that means is along this curve here, x prime is equal to 0, which is the same as this one. And if it helps, I can put this all in red if you like. Along this curve, we have that there's no change in x. And if we take and we graph this curve just as an example, like I'll put over here an xy plane, and then I'll put a curve. And this will just be a general curve. It won't match up like to any particular, well, it will match up to a set of particular values, but those values I'm just kind of randomly choosing because this is a general formula, but I just need to show something. So there's not a lot of thought I put into what the curve of this line is. It's just an example. Now along here, what you can do is you can think of the slopes not changing in terms of x, but they would change in terms of y. So what you might see along here, if you think in terms of a slope field, you know, with the slope field, you have these different slopes everywhere and so on. Well, what's going to be the type of slopes on the line? They're going to be slopes with no change in x. So they might look something like this. Might be going up or they might be going down. You have some combination, but whichever. They're going up and down. They're not going left and right. And that's because there's no change in x with respect to time. Likewise, with this curve 0 is equal to y prime, what that's saying is there's no change in y with respect to time. Hence, if we were to just graph a sample line, we might have something that kind of looks like this. And now here, there's no vertical change. The change in y with respect to time is 0. So what happens is you only have curves that are, or I should say only have slopes that are looking to the left and right. It looks kind of something like this. Now you can use these to kind of imagine what's going to happen with the different solution curves. For example, if we take and suppose we start a curve, let's say here, based on what's happening with these curves, just take a guess just to see how your intuition is. And if you would say it in chat, you can say it publicly or just say it privately to me, whatever you like. If you look at this starting point and you trace through time, you go forward in time, is this curve going to go like this? Is it going to go, like this? Kind of describe for me, if you would, what's going to happen with this curve? Or what do you think is going to happen? I'm not judging for whether you're right or not, just to kind of see what your thoughts are and just to make sure you're kind of following somewhat. And if you really have no idea, we can just talk about it. So where do you think this is going to go, just based on your guess of comparing it to these Nullclines? Okay, those of you who gave me feedback, appreciated, even if it's just no idea. I still appreciate it, just to have an idea where you're at. Now, we'll have an applet that will allow us to, have a computer compute exactly or very close to exactly what's going to happen. But my guess would be, looking at this, that I think we sort of have slopes that are probably positive up to the right when we're around this nullcline, around the red nullcline. And then we're probably going to have something that maybe looks like this, kind of over here. If I just sort of imagine filling in a slope field. So I think it would do something like it'll be heading to the right, but then maybe also going up a little bit and might do something like that. That's what I think is going to happen. But we'll see for sure in a second. But it's good just to kind of get an intuitive sense of what's going on here. Now I'm going to draw a new curve, maybe in a different color. And I want you to tell me whether you think this is possible or not. So here's a new curve. Could this possibly happen? Why could it happen if you think so? And why couldn't it happen if you don't think so? So say we had a different solution curve like this. Actually, let me go like this. Could this be possible? This magenta curve. Why could it be or why could it not be? Just your thoughts. And again, it's giving you time to sort of work through the intuition here before we just jump into the applet and just start punching numbers in without thinking about it. And even if you're not sure, you can say that too. Just gives me an idea of where you're at. Okay, for those of you who gave some feedback, thank you. I appreciate it. Makes it a lot easier when you give feedback, because then I know what you're thinking, and then I can adjust. So imagine you look at this spot right here, like this point. At that point, when it crosses this red nullcline, the nullcline, which is x prime is equal to 0, at that exact point, there is no change in x, or there should be no change in x, because we're on this red nullcline. So the only change should be vertical. The solution curve should only be going up or down. And that looks like what's happening here. So that's okay. However, there's a problem down here. At this spot, maybe it kind of looks like the slope is roughly like this. That would not be possible, because when you cross this green nullcline, you should only be going to the right or to the left. But that is definitely not what happens here. We pass through it in a vertical sense. There's at least some non-zero vertical component. So for that reason, this magenta curve has a problem here, and so you wouldn't see something like this. So I'm going to get rid of that. And I'm guessing what would kind of happen with this magenta curve, based on the way I've drawn this, if it kind of is going down like this, it might kind of go like so. And then because of this curve right there, it might do something like that. But again, we're just kind of getting the intuition. This is not super exact. Now, with that said, what I'd like to do is open up the applet now that we've talked about this a little bit. So let me go ahead and do that. Okay, here is an example of the applet. They're the green and the red nullclines that we just looked at previously. So let me do some annotation. If we take x prime is equal to y, and then we say that that should be 0, so that we have 0 is equal to y, which I'll type in a second here. Then what we have is exactly this nullcline here. Actually, maybe that would be better in a different color. So we have this nullcline. That's where y is equal to 0, of course. And then the reason the arrows are going up and down is because we have no change in x, just like what we were talking about. There's also the nullcline that looks like this. It's y prime is equal to x in this particular case. And then that means that x is equal to y, or x is 0 is equal to x. And that's what gives us this nullcline here. Now what we can do is we can imagine taking a starting point. For instance, I have up here x of 0 is equal to 1 and y of 0 is equal to 1. That means when t is equal to 0, the x value is 1 and the y value is 1. We can then imagine starting at the point 1, 1, which I think would be roughly here. I think each of these hash marks are 0.5. And then we can take and update this graph. And what it will do is it will, oh, that worked nicely. It will take and plot the solution curve that starts at that point 1, 1. And this kind of makes sense because of the way these nullclines are. It looks like it's pushing us both to the right and up. And it looks like they're weighted roughly the same so that they will go up at the same rate. Now, what I'm going to do, just to kind of show you a little bit, is change the weights, quote unquote, for some of these and see what changes. So imagine I start at the same point, but I'm going to clear this curve. Now imagine I weight these differently. So I weight the y prime a little heavier. I update the graph, and now notice the nullclines didn't change their positions, but we do have a change in this curve. And that's because we have the y prime now, quote unquote, weighted more, the y prime curve. So what I'm talking about is the fact that I changed that to a 2, where before it was a 1. So there's sort of more push, quote unquote, from one nullcline than the other. So you won't necessarily see how much weight or heft each of these nullclines have. So they just give you a rough idea on what the solution curves look like. But with this applet, we get something a little more exact. Now, for the first part of this lab, what you want to do is the following. You want to go to the lab itself. So I'm going to clear all of this. You want to go to the lab itself and you want to try to recreate. You don't have to actually do it exactly. You don't have to get the slopes exactly for each of these, but you want to get the general behavior. So for instance, you want the two nullclines to be roughly like this, so that as it says, all the solutions diverge out to infinity. And just a little note that again, what you have is that you start at these points and you move away. So you kind of have, this is moving away from here, this is moving away from here, this is moving away from here, and so on. So that's the behavior you want to try to get, is this kind of moving away from the origin for the first one. And then there's several others with different behavior. So for the second one, you have this, where the solutions move in towards the origin. They get sort of pulled in, if you will. C, there's the saddle behavior, where it sort of approaches the origin at one point and then moves away. So just to make it a little more clear, what you would have is kind of something like this, where you would be approaching the origin, and then after a certain point, you kind of round this bend and then start moving away. Kind of look like this. And again, you don't need these exactly the same, but let me say one more thing before I let you just kind of try to find these for a bit. If we actually go back here, you may remember that I set up this general notation that x prime, because there's no change in x, the x prime curve is equal to, in general, ax plus by. If you start rearranging that, what you end up with is that negative a divided by b times x. Let me maybe put that all in one thing there. You have that negative a over b times x is equal to y. Now that's for this red curve. If you look at the slope of this red curve, that slope looks to me very roughly to be, maybe you go kind of looks like you go over 1 and down 3. So it's going to have a slope of negative 3. So that means negative a over b should be negative 3. And now you could choose your a and b so that you get a slope of negative 3. You've already got the negative. So you could do something like you could let a be equal to 3, and you could let b be equal to 1. That would give you the slope of negative 3. And I think you'll find if you go to the applet, which I'll jump back to now, if you go to this and say that this is 3 and then 1 and update this, you'll get exactly the slope you want here. And again, you don't need to be exact. You just need to be close enough so you get the right behavior. So let me give you 5-ish minutes to kind of experiment and try to find the right coefficient so that you can get each of these systems with their particular behavior. And of course, feel free to private message me if you've got questions. I'll just give you some time to work. I want to chime in here. Someone asked a question about getting the arrows to switch directions. Well, actually, 2 students did. And I want to say, I can't remember what I had this to start with. I think it was 1 and 0. But if you look at least at my screen, notice that when I first set the red curve, like we did the computation to get the red curve slope. Now the slope of that curve itself, even though it's a curve of slopes, but the slope of the red line, if you will, it has the right slope, but the arrows are not matching up. That the arrows up here in the second quadrant are pointing down, in the fourth quadrant are pointing up. Now notice I'm not going to change anything with the first equation. I'll just change the second equation so that its slopes align properly. And if I do that, just from changing the second equation, now the arrows from the first one, they switched. So the arrows will have to do with how the 2 equations relate to each other. When you first set up the coefficients, you'll only want to worry about the slope of the line itself. The arrows will come from making sure that the 2 equations align with one another properly. So I just wanted to say something about that. So if you want the arrows of one to change, you might want to vary the coefficients of the other. And again, you don't need to get the graphs exact. You just need to get them close enough so that the general behavior is the same. Okay, I want to jump in here just for the sake of time so that we can kind of talk through some of the rest of this. Would you let me know, private or public chat, either way, how many of these you think you have found the right coefficients for to get the right behavior? So it looks like there's A, B, C, D, E, F, so 6. So of the 6, how many do you think you have so far? Just to get a sense of where everyone's at. I mean, we're going to go forward either way, but I'm just curious. Okay. We're getting a mix anywhere from 1 to 6-ish, common being 3. All right, so you're at least into it somewhat. And if you're having difficulty, you can let me know. Maybe after class, I can try to help you a little more before the next session. But let's talk about where to go from here. let's see. So where we want to go from here is to talk, like this is essentially 2, problem, or number 2 in the lab write-up. Then when we look at 3 and 4, they both have to do with the trace and the determinant. I can annotate this, should work nicely. So if we take the system, I'm just getting the text ready here. If we take the system x prime is equal to 3x plus y, and we take y prime is equal to x, or maybe 1x plus 3y. If we take this system that I've written on the screen here, then we can create a matrix. And the matrix would look like this. We can call it A or M, call it whatever you like. That's going to look like this: 3, 1, 1, 3. Now, we talked about in recitation for sure, and I'm sure you talked about besides that, or seen in the videos that Dr. Bennett posted, that we can compute the trace and determinant of A. The trace of A is going to be equal to 3 plus 3, which is equal to 6. The determinant of A is going to be, according to the determinant formula for 2 by 2 matrices, 3 times 3 minus 1 times 1, which is, of course, equal to 8. So for this particular system that I've drawn here, we have a trace of 6 and a determinant of 8. What you want to do is compute the trace and determinant for your system in each of the cases that you come up with. There are 6 of these different cases. You'll want to compute the trace and the determinant for each of the 6 as you go through them. So the first thing is to make sure you're getting the right behavior to find what the coefficient should be. Then the next thing you'd want to do for each of these is, as I mentioned, compute the trace and the determinant. I'm just double checking. So then what you want to do is you want to say, or you want to try to see what relationship there is between the trace and determinant and the type of behavior you get. And when we say that, the type of behavior you get in general. For example, I'm going to put at the top of the screen, if we have trace A is equal to 6, and then we have determinant A is equal to 8, then that set of values gave us solutions. How do I want to say it? Solutions diverging from origin to infinity. So this should appear at the top right. So that's one case we have. Now the rest of this I'm going to get rid of, and we can look at a different system. Actually, does anyone want to suggest what they got for B, if you think you've got the right coefficients? I could futz around with it, but just for the sake of time, maybe you've already got them. Does anyone think they have the coefficients for B? Want to chat me that, and I can enter them in and we can do a test? So I'm just going to go with the first one I see, and we'll see if this works. Yeah, that looks pretty good to me. Okay, cool. And I'm actually going to start this a little farther out. So let's do that. Yeah, that's looking good. All right, cool. Oop. Now, if we compute the trace and determinant here, we can add that as well. And now we have solutions getting pulled in towards the origin. So instead of diverging from the origin to infinity, they're getting pulled in towards the origin. And if we computed the trace really quick there, we've got what? the trace of A is going to be equal to -3. And then we have the determinant of A is going to be equal to, let's see, 2 minus 1, which is 1. And that's where the solutions converge to the origin. And if it's not appearing on your screen, it should be now. Okay. For A and for B, we have computed trace determinant, and then we've seen what the behavior does. If we keep doing that, perhaps it will show, perhaps we'll have enough data to be able to make a conjecture about, oh, if I see that the trace is such and such, the determinant is such and such, or they're related in some way, then I can predict that you're going to have, converging to the origin. I can predict that you're going to diverge from the origin to infinity, or spiral around, towards the origin, or spiral away from the origin, or, be locked in a perfect oval. And what I might suggest is to, how do I give a good hint that doesn't just totally give it away? I might suggest, yeah, sorry, I'm towing a line here between hint and giving it away. Yeah, I guess the only thing I'll say is you might want to consider various types of algebraic relationships, such as you may say, oh, when the trace of A is greater than the determinant, this is not necessarily going to be useful, but just to give you a sample, you might say when the trace of A is the determinant of A, I predict that means we'll have solutions converge. That might be a possible conjecture. Or, as a different example, to show the kind of things you can do, you might say that, oh, when 4 times the trace is larger, or is, let's say, less than the determinant, or something like this, then that means that solutions will spiral inward. And I'm going to have that pop up. So you can do things like this, and I'm not claiming either one of these will be accurate, or maybe they both are, I don't know. But these are just the types of things that you'll want to do as far as establishing relationships. Or you could say when they're equal, maybe something happens, or blah, blah, blah. Maybe you want to add another coefficient in here. Like you could say the trace of A, maybe when it's greater than the determinant of A plus 7 or something like this. Then that means blah, blah will happen. This is the type of thing that you're kind of looking at. And that's really it I have for explanation for the lab. So I will leave that for the day. You're welcome to stick around for a few minutes if you've got some questions to ask me. Otherwise, you have a good day. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.